Welcome back, ladies and gentlemen. In this video, we'll talk about potential and kinetic energy and also the conservation of energy. Okay, so first of all, energy, we know that there are lots of different forms or types of energy, and these different types or forms just transfer between each other. Okay, so we put gas into our car in the form of chemical energy, and the stored energy in the chemical bonds of gasoline, we explode it to make motion or kinetic energy in cars. Okay, we do that within our bodies as well. Okay, the two main forms of energy that we'll talk about in this video are potential and kinetic, and how energy changes forms between those two different types. Okay, first of all, just a definition. Energy, we define energy as the ability to do work. It is a scalar quantity. The units are the joule, the same as work. The two types of mechanical energy that we'll talk about in this video are gravitational potential energy and kinetic energy. These two formulas are on your formula sheet. For potential energy, we have three things: mgh. M is just our mass, g is our gravitational constant, and h is the height above some reference point. And I'll comment more about that when we get to our next video, but our height needs a reference point when we're talking about potential energy. Okay, with kinetic energy, that is the energy of motion, so 1/2 mv squared. So it's a moving mass, so 1/2 times the mass times the velocity of an object squared. Okay. We have this thing called the work energy theorem, and that says, hey, if we do work by a net force on an object, that's going to change the kinetic energy of an object. If we think of a person on a bicycle sitting still, and they all of a sudden apply a force to their bike, they're going to start moving. So their kinetic energy will change when we start doing work on an object. Okay, so here's an example where we have a 1,000 kilogram car. It's going 20 meters per second. It brakes and comes to a stop. So how much work is done? What happens to the energy? Okay, so the work done is going to be, how much work is done is going to be the change in kinetic energy of an object. Okay, so the initial kinetic energy minus the final, we can look at doing 1/2 times mass times our velocities, our final velocity squared minus our initial squared. Okay, the amount of work that'll be done on this car would be negative 200,000 joules. Okay, and where does that energy go? That energy is, that energy, or NRG, that's my short form for energy. That energy is, it's lost as heat. Okay, so we apply brakes, and friction applies to the brake rotors of a car, and it brings it to a stop. So those brakes get hot, and that energy gets dissipated as heat. Okay, so we can take this a step further and say, hey, if the car takes 32 meters to stop, what is the average stopping force applied by the brakes? Well, we know that the amount of work is equal to force applied over a displacement. Okay, in our case, the work done is negative 200,000 joules. We can take that and divide it by the displacement that the car goes through. And we find that the amount of force that's needed to stop the car is 6.3 kilonewtons. And this negative here that we solve for with the math of it, that just tells us the direction that the force is acting on the car. Okay. Okay. Next, we'll talk about combining those two energies together. And before actually, maybe I'll show you this formula first. So the big idea is that the energy of an object cannot be created or destroyed. It can only change form. So we've got a big formula that looks like so, and this formula is on your your formula sheet, sorry. And we will add to it in a little bit. If you look at your formula sheet, you'll see a couple of other works on there. So we will add to it by putting work in and work out later. But for now, that red box is telling us that, hey, our initial total energy has to be equal to our final total energy. And I'm going to skip over to this thing that you can Google. It's called the FET Energy Skate Park, and it's something that looks like this. And I'm going to talk about three different things on this screen. So here is a skateboarder that's just going up and down a ramp. First thing I want to bring your attention to is the total energy on this bar graph. So over at the side, you can go and click bar graphs to show what the different energies are doing. On this bar graph, we have kinetic, potential, and thermal energy. So the total energy of this skateboarder does not change. Okay, we see that the forms of energy are changing between kinetic and potential. And we have also made this the perfect physics world where thermal energy is 0. Okay, and you can go and change what you, or the amount of friction that's acting on this track. You can go and turn this into lots of friction, and we just know by experience, eventually that skateboarder is going to come to a stop. Okay, so for now though, I'm going to turn friction off, get the skateboarder going, and just pause it in a couple of spots. So at the very top of this motion, you can see that the kinetic energy of this object is 0. Kinetic means moving, so 1/2 mv squared. The velocity of the skateboarder is 0 at the top, so the kinetic energy of the skateboarder will be 0 at the top. At the bottom is where the kinetic energy will be the maximum. Okay, and that's why all of the skateboarder's energy at the bottom is going to be kinetic. Okay, and then we can see how that fluctuates up and down as the skateboarder goes. Okay, the potential energy of this skateboarder, same thing, we can pause at the top and look at, okay, at the top, the skateboarder is going to have maximum potential because that is where the potential energy of the skateboarder is at its maximum. He's the highest he can be above this dotted line. I'm hoping that you can see that on your screen. So PE equals 0 at this dotted line. This is that reference line, or that reference point that I was talking about in the formula for potential energy. So if we hit play again, just to show you this, we can actually change where our potential energy is 0 at this dotted line. And just so you're aware, like, we can have negative potential energy. We can have negative potential energy. It just means that it's negative relative to some reference point. Okay, and this becomes of more importance in later courses when you're looking at gravitational potential energy of celestial bodies. Okay, if we flip back over here, the next few questions, we are just going to be applying this big long formula, and the big long formula is just telling us, hey, our initial total energy is going to be equal to our final. Okay, so here's an example where we have a 2-kilogram ball. It's dropped from the top of a 40-meter building. So we're going to be looking for how fast the ball is moving just before it hits the ground. So this will be its final. This will be the ball's initial spot. So we're going to be looking for the velocity down here. What is the velocity of that ball just before it hits the ground? Now, some cool things are happening here. So at the top, we know that if we drop the ball, the velocity is 0 when we just let go of that ball. So the kinetic energy will be 0 at the top of this object's, or at the start of the initial part of this object's trajectory. Sorry, I stumped for a word there. Okay, and then at the bottom, generally we're going to take our reference point to be, this will be our height, or our reference point. We'll call this our height is 0 because it makes it nice and handy that our height at the bottom will be 0. So if we think about this, if our velocity at the top and the left and right sides of this formula just represent our energy at the top, energy at the bottom. Okay, so our kinetic energy at the top is 0. Our potential energy at the bottom is 0, and we're left with mgh at the top is going to be equal to 1/2 mv squared. Okay, and before we start plugging and chugging numbers, I'm just going to cancel out my mass, because mass is the same at, mass is on both sides. We can cancel that letter out. We end up, if we plug and chug, we'll end up with finding velocity. We'll find that velocity is equal, or v squared, is equal to 2gh. And if we plug and chug, we'll get v squared is equal to 784. Okay, if we take the square root of both sides, we'll find that our velocity at the bottom, just before it hits the ground, will be 28 meters per second. Okay. Okay, so next, what if we have a farmer who's maybe he's a little disgruntled and wants to retire an old tractor by driving it off a 12-meter cliff? Of course, he jumps out of the tractor just before he sends it off the cliff. So he's sending this tractor off the cliff at a speed of 50 meters per second. So the first thing we'll do is we'll take that, 50 kilometers per hour. Okay, we'll divide that kilometers per hour by 3.6, and we'll find that the initial velocity of this tractor as it flies off the cliff will be 13.8 repeated meters per second. Okay, and that's going to be important because this tractor, as we know, is going to fly, and then when it hits the bottom, it'll explode. So we're going to be looking at just before this tractor hits the ground will be our final spot. Okay, so our potential energy at the bottom of this tractor's trajectory is going to be 0. So this whole term is going to go away. Okay, the other nice thing, again, we have mass in every single term, so we will cancel those out. Okay, and we're left with just plugging and chugging some numbers. So at the top, we've got gravity times our height above the ground. It's going to be equal to our, that's going to be, we forgot our kinetic energy at the top. So that'll be 1/2 times 13.8 repeated squared. That will be equal to our 1/2 v squared. We're solving for our velocity at the bottom of this tractor's fall. Okay, if we plug and chug this through, we should get that v squared is equal to 428, and that v is 21 meters per second just before it hits the ground. Okay, and just going to ask, does that make sense? Well, if the car is going to have an initial velocity of 13.8, I mean, we could use kinematics or projectile motion to solve this thing. We could find the velocity of this object at the bottom by using projectile motion, but our conservation of energy is just a much more efficient and cleaner way to get there. So does it make sense that our velocity at the bottom is 21? Well, yeah, it has to be more because more than what it started with, because it's falling. It's going to be gaining velocity in the y direction. Okay, so this question is done. On to the next one. Okay, what happens if we have a soccer ball? So soccer ball, we're given its mass, it's kicked through the air. So this is a situation where we've got a soccer ball, it's being kicked with the speed of 15 meters per second. Okay, we're going to call our reference point of 0 the ground. So this thing will have a trajectory that'll look something like so. So part A is asking, when this height is 4.0 meters, what is the velocity? I'll make that part A. Part B is saying, hey, when this thing is going, like if it's at this point, it has a velocity of 5 meters per second, what is this height? Okay, so two different questions, but the same kind of situation. Okay, so in part A, again, we're going to get mass that cancels out in all of these terms. So our potential energy initially for this ball, it's going to be 0. Okay, so if we plug and chug through some numbers, our 1/2 times that initial velocity is 15. Okay, that's when the ball is just kicked. Okay, that's going to be equal to 9.8 times, in part A, we're told that, hey, this ball is 4 meters above the ground. What is its velocity at that point? This is what our equation should look like. Okay, so if we go and plug and chug some numbers, we should get something like this. Okay, if we go and solve for v squared, we'll end up with 146.6. Okay, if we square root that and chop it for sig figs, we'll get that our velocity at that height is 12 meters per second. Okay. In part B, we're going to start with a similar thing. Our potential energy to start will be 0. Okay, and then we'll cancel out our masses because they're in every term. Okay, so our plug and chug becomes 1/2 times 15 squared. Now in this case, we're trying to find our height at some spot where the velocity of this ball is 5 meters per second. So that'll be its after or its final snapshot that we're looking at. So our formula will look like so. Okay, if we go and plug and chug this through, we should get h is equal to 100 over 9.8, or h is equal to 10 meters. Okay. Okay, so big idea. We have to take 2 snapshots, an initial and a final spot that we are analyzing, and then apply our idea that energy is the same or constant throughout every spot of this thing's motion. Okay, so your turn. Here we have Tarzan. Tarzan is an 8-man who is swings from a branch that's 3 meters above the ground. So you can think of like, here's our Tarzan. He's going to be swinging from a branch that's 3 meters above the ground. Okay, we know that Tarzan's going to swing. Okay, so part A is saying, what is his velocity at that point, just as he passes by the ground? Okay, part B is saying, okay, well, how high will Tarzan swing to? So what is his height if he is swinging? And oh yeah, he's swinging, we can't forget that he has an initial velocity, right? So this is 5 meters per second. So in this case, Tarzan initially will have both PE, or potential energy. Tarzan will initially have both potential energy and kinetic energy. Okay, and then we're asked to find a couple of things in questions A and B. Okay, in part C, it's a separate jump. So here we have Tarzan that's leaping from a tree, but we don't know his velocity. We're saying, hey, what does that velocity have to be so that when he swings down and comes back up, he's going to end up 4 meters above the ground? Okay, give those a try and answer those on your screen. Okay. Okay, folks, you can check your answers with answers that are on your screen. There are energy and conservation of energy questions to give a try. Please give those a whirl, and I'll see you again soon.